Welcome everybody. This is the explanation of the mock exam and I will go through all the questions one by one. And question one is the question where we have two complex numbers and we want to have the multiplication and the result of the rotation when we multiply the first complex number with the second. Now we have Z1 is equal to 3 plus 3 times j, and Z2 is equal to 2 minus j, and if we multiply these two we get 3 plus 3j times 2 minus j is equal to 6 minus 3j plus 6j, and then 3j times minus j is 3 is equal to 3, plus 3 is equal to 9 plus 3j. Now the multiplication with the first and the second one, so if we have Z1 is R1 theta 1 and Z2 is R2 theta 2, then Z1, Z2 is equal to R1, R2 theta 1 plus theta 2. So if theta 2 is positive, we'll get the rotation anti-clockwise and counterclockwise, and if it's negative, we'll get it clockwise. Now, so we need to find out what theta 2 is. Well, theta 2 is the arctangent of minus 1 over 2 is equal to minus 0.46. What is very important here is that you plot Z2, which is somewhere here. What is it? 2 minus j? No, so it's here. So we already know that this angle theta 2 is going to be negative. So the rotation is 0.46 radians and it will be clockwise. So this was question 1. Now we shall go to question 2. Here it is, where we have a fraction and we have to perform partial fraction expansion. So let's start with that. So question 2 is equal to, so xs is equal to s squared plus 8s plus 11 divided by s minus 1 s squared plus 6s plus 13, and we have two factors, a linear factor which repeats 1 and a quadratic factor with complex roots. So we will write this down as a over s minus 1 plus bs plus c over s squared plus 6s plus 13, and then we multiply this with each other again, so we get the same denominator. So we get a s squared plus 6s plus 6 a s plus 13a, and then we multiply s minus 1 with bs plus c plus bs squared plus bs plus c s minus c over that same denominator, and apparently this has to equal s squared plus 8s plus 11 over that same denominator, which gives us three equations because we have factors, coefficients for s squared, and they have to match the ones on the right. The coefficients for s and the constants all have to match up. So a s squared plus b s squared must equal 1s squared. Then we have 6a minus b plus c equals 8. And we have one constant coefficient, 13a minus c there is equal to 11. Now I will take the first one and I will say that A is equal to 1 minus B. So I can put that in here. So, well actually I'll put that in here. So 6 minus 6B, that is equal to 6A, minus B plus C is equal to 8. So I can group these two together and the 6 goes over that way. So I have minus 7B, which I'll take to the other side, 7B, and I have 6 and 8 plus 2. Now, this formula for A, I'll put in there, and this formula for C, I'll put in there, and I will get 13 minus 13B minus C, so minus 7B minus 2 is equal to 11. Now, if I clean this up a bit, I get 11 minus 20B is equal to 11, and that can only happen if B is equal to 0. And if B is equal to 0, then A is equal to 1 and C is equal to 2, and our partial fraction expansion will be A was equal to 1 over S minus 1 plus, well, B is 0, C is 2 over S squared plus 6S plus 13. And we are done. Question 3. We have that Z to the power of 3 is equal to 27. Well, first we will write Z as R with angle theta, which means that Z to the power of 3 is R to the power of 3 with angle 3 theta, and 27 can be written as 27 with angle 0 plus 2k pi, for k is 0, 1, 2, etc. But because it's a third order equation, we will have 3 solutions, and I'll take k is 0, 1, and 2. But we're not quite there yet, so if 27 has to equal Z to the power of 3, we get R to the power of 3 with 3 theta is equal to 27 with angle 2k pi, because the 27 in the complex plane is on the positive real axis and has argument of 0. So if these are equal, then R to the power of 3 must equal 27, and 3 theta must equal 2k pi. And, well, if R to the power of 3 is 27, that means R is 3, and our angles will be theta equal to 2k pi over 3, for k is 0, 1, and 2. And we can write out our solutions. For k is 0, we get 3 with angle 0. For k is 1, we get 3 with 2 pi over 3 as argument, and for k is 2, we get 3 with 4 pi over 3. And these are already in polar form, so we are done with question 3. And I didn't show you that one, but I will need it for the next one, because we have a mass spring damper here, where we want to determine the differential equation that is associated with this. And I'm wiping out the board, so we have a fresh board. If we look at this, there are 3 forces which I will now explain. So we start with the second law of Newton, that the sum of the forces is equal to the mass times acceleration. We had 3 forces. If we go back, we have the spring force and the 2 damper forces, and we also have F of t. So we have, well, the spring force will be directed to the left, so that's minus K1x minus, did I use B or C? I used C. Usually I'd use B, but it doesn't really matter. These are the forces from the springs and the damper. We have Ft, which is a positive force, is equal to m times the second derivative of the displacement. And if we gather this all together, we get m x double plus b1 plus b2 x prime plus k1 x is f of t. And that really concludes question number 4. If we go to question 5, we are asked to find the damping ratio and natural frequency for x prime plus 3, x double prime plus 3 x prime plus this. Now we can do this in 2 ways. We know that omega n is the square root of k over m, and zeta is b over 2 square root of k times m, and we can just simply fill in these values, and as our m is 1, our k is 2, we get this is equal to the square root of 2. This is equal to 3 over 2 times the square root of 2, and we can leave it like this. Now, if we look at this equation, then we know that this is larger than 1, so the system is over damped. Yes, because the square root of 2 is about 1.14, and that is less than 3. You can also see it differently, but we'll leave it like that. And then we have question 5. And I see that I didn't switch to the right board, so I'll do question 4 again. Question 5. We have x double prime plus 3x prime plus 2x is f. We can use these formulas for omega n and zeta, and if we fill in the coefficients, we get square root of 2 and 3 over 2 times the square root of 2, which is larger than 1, so the system is over damped. You could also rewrite this in the form x double prime plus 2 zeta omega n x prime plus omega n squared x is f of t. So this is in a standard form, and then you also see that omega n must be equal to the square root of 2, and there's a bit of calculation involved to get zeta, but you get to the same values. The next question, question 6, is basically to solve this differential equation where ft is equal to 5 for t larger than 0 and 0 everywhere else. So this is a step function. So we have this differential equation with this f, and we're going to solve it using the Laplace transform. So we take the Laplace transform of what we're doing on the left-hand side and the Laplace transform of the right-hand side, and we see that we get s squared plus 3s plus 2. Oh yeah, and all the initial conditions are 0, is 5 over s. Now we divide left and right by this to isolate x of s. So this is step 2. Step 1 was the Laplace transform. Step 2 is isolating our x. Next we'll have to write this as a partial fraction, but before that I will factor this one out, because it is a quadratic factor with real roots, so I can factorize it like this, and our partial fraction expansion will be a over s plus b over s plus 1 plus c over s plus 2. Now the calculations to get a, b and c, I will, well, why not? So a I multiply by s plus 1 times s plus 2, which is equal to that. So we get s squared plus 3a s plus 2a. b I multiply by s and s plus 2. So that is s squared plus 2s. So I get bs squared plus 2bs. And c I multiply by s and s plus 1, so that's s squared plus s. So plus cs squared plus cs, and that has to equal 5 because they have this same denominator now. Again, I get 3 equations. I get everything for s squared, so I have as squared, bs squared, and cs squared, and here I have 0s squared. So I get a plus b plus c equals 0. I do the same for the coefficients for s, 3as plus 2bs plus c. So that is 3a plus 2b plus c is also equal to 0 because on the right hand side I don't have any s. And then I have 2a here, and that's it. 2a equals 5. And then we start calculating for, I'm going to call this 1, 2, and 3 so that I can say things like 3 implies that we have a is 5 over 2. And if I take the third equation and subtract the first equation, I get, so 2 minus 1 gives me 2a, b minus 2b minus b is b, and this c that cancels out, so we get this equation, and this makes my life a bit easier, because if 2 times a, which is 5, plus b is 0, then we have b is equal to minus 5, and if b is equal to minus 5 and a is equal to 5 over 2, then c must equal 5 over 2. And we're pretty much done now, because now we can fill in these coefficients. And I'll just continue like this. Is 5 over 2 times 1 over s minus 5 times 1 over s plus 1 plus 5 over 2 times s plus 2. And if we take the Laplace, the inverse Laplace transform, we get x of t is 5 over 2 minus 5 e to the power of minus t plus 5 over 2 e to the power of minus 2t. And this is our question 6, and that's one of the longer ones. All right, then we shall go to question 7. While I wipe out the board again. And here we have a block diagram, and the question here is to solve this block diagram. All right. We have our input f, which turns into an error. We have a block I and a block P, suggesting that this is a PI controller. That doesn't really matter for this exercise. We have our output Y. This goes back to some block H, and we have a minus here. Well, the first step is to simplify this block. Here I have 2 parallel systems which give me an addition. So this becomes I plus P. And now I have 2 cascaded systems which yield a multiplication. So I plus P times G. And now I will name, so the output I know is equal to G I plus P times the error. And my error is equal to my input minus h times the output. And I substitute this in there, and I get y is equal to g I plus p times f minus g I plus p h y. And what I do is I take this term, move it to the left, so I have 1 times I plus g times I plus p times h times y is equal to g I plus p times f, but I'm looking for the transfer function, so I want to have y over f, and that is equal to g I plus p over 1 plus g I plus p times h, and we are done. So we'll go to the next question, and here we have a specific transfer function. So we have, I'll just copy this, 2s minus 1 over s squared minus 4s plus 5. So now we've copied this, and the question is, give the closed loop poles. Well, the poles are the points s where the denominator is equal to 0. So we have s1, 2 is minus b plus or minus the square root of b squared minus 4ac. So b squared is 16, minus 4 times 5 is 20 over 2. The 16 minus 20 is equal to minus 4, and the square root of minus 4 is, well, plus or minus 2j. 4 over 2 is 2, so this is equal to 2 plus or minus j, and they are in the right half plane, so this system is unstable. The behavior will be that if we have a step input, because it's unstable, we'll get exponentially growing oscillations. So what we'll get is that we'll get this kind of behavior. All right, that was question 8. We have 3 more to go. Here we have a block diagram where we get given an expression for our controller. And we've pretty much covered that if we have some kind of controller and some kind of system, and we have our output with our error here, and we have a minus sign there, then we know that the closed loop system is c times g over 1 plus c times g. We can do that by giving E a name, and we know the output is G times C times E, and the error is simply the input minus the output, and then we get this. And if our controller is Ki times S, we get Ki over S times G over 1 plus Ki over S times G. And to tidy this up, I multiply the numerator and the denominator by S, and we get Ki G over S plus Ki times G, and this tidies it up a bit better. So going to the next question, here we have a different controller, but we also have a value for the plant. And we basically use the same thing here, where we have C is Kd times S, and G is equal to 1 over S plus 2. And we can fill in this system again, is equal to Kd times 1 over S plus 2 over 1 plus Kd times S over S plus 2. Now, to clean this up, I am going to multiply the top and bottom by s plus 2, and we get kd times s over s plus 2 plus kds to get our closed loop transfer function, and I'll just write this as kd plus 1 times s plus 2. So we've rewritten our system, and is this system stable or not? We look at the closed loop the closed loop poles, and that is kd plus 1 times s is equal, plus 2 equals 0, and that is the case for s is equal to minus 2 over kd plus 1. And as this is always negative because kd is always positive, these are in the left half plane, so the system is always stable regardless of the value of kd. Final question, where we have another controller and we have been given a closed loop transfer function, and the question here is for which value of kp is this system critically damped? And let me just copy the transfer function, and that is s squared plus 6s plus 2 plus kp. That is our closed loop transfer function. Yes, and here we go. This system is critically damped if both poles lie in the same spot. So we have, if we have our two poles, they are equal to minus b plus or minus the square root of 36, that's b squared minus 4 times 2 plus kp over 2. So these are the two closed loop poles, and it is critically damped if we have that, we only have one pole. So this square root must equal 0. So 36 minus 4 times 2 plus kp must equal 0. And we could also see that the system is critically damped. Critically damped for b squared minus 4ac is equal to 0. Or sorry, we could, that's the criterion. If that is 0, so we have b squared minus 4ac, and a in our case, a is equal to 1, and this is the case if, well, we can write minus 4, 2 plus kp is minus 36, so 2 plus kp, it must be equal to 9, and that's the case for kp is equal to 7. So this requires you to understand what critical damping is, so that must imply for a second order system that we only have one pole, and if you have one pole, this square root must be equal to 0. So this is very quickly these are the explanations and the answers for the mock exam.